Hello everyone, thank you for joining today. My name is Manam and today we're going to be looking at momentum. So we have a couple of learning objectives, and that's to be able to define and understand what momentum actually is and to be able to recall that momentum is a conserved quantity. So if you're ready, let's get right into it. Now, first of all, what we want to understand is what actually is momentum. Well, momentum is actually just a physical quantity that's represented by the multiplication of mass and velocity. So you can see here that my fire truck, right, it's speeding along, it has mass and it is going at a velocity, hence it's speeding, and so therefore it has momentum. So whenever we look at momentum, what we're really looking at is speeding objects, okay? Speeding or slowing down objects. So you'll notice that momentum is usually described when we're thinking about objects that are really in motion, and then also when objects collide with each other, okay? So first of all, let's actually look at the momentum equation. So momentum is given the Greek symbol just the symbol P, right? And that comes from the Greek word of impetus. Impetus meaning the sort of characteristic of movement, right? Bringing movement into something. And so that kind of makes sense, right? Because when we're looking at momentum, we're looking at moving objects. Now, momentum is P equals mv. Now, let's have a look at our questions first. So mass, as always, just a standard unit. It's in kilograms. Now, velocity is again in meters per second, and you can see that we're just multiplying these two units together, and so our units for momentum end up being kilogram meters per second. Okay, so that's our unit right there. Now, what we also need to understand is that momentum is a vector quantity. So this means that not only does it have magnitude, it also has mass. So really this means that if we're looking at, say, the collision between two cars, so I'm going to quickly draw two cars here, and right, and they're both speeding this way and this way, both of these cars will have some kind of momentum, but one of these values will be negative. Now, the convention is usually going left is negative. So if I say that this car here has a mass of 100 kg and it's going at 10 meters per second, if I multiply these together, that gives me a momentum of 1 times 10 to the 3 kilogram meters per second positive. And say it was the same for the other car, 100 kg and then 10 meters per second. I've forgotten the wheels for the cars, but oh well, you understand what's going on here. Again, I multiply these together. This ends up being minus 1 times 10 to the 3 kilogram meters per second. Now, this brings me on to my second feature of momentum. Momentum is always conserved. So what does this mean? Well, this really means that momentum before a collision is always equal to momentum after a collision. Usually we give these values of 0, right? So now let's have a look here. Now, momentum before my collision is actually 0, right? Because we're not Now, momentum before my collision is 0, but students often get confused about why that actually is. Well, what you need to remember is that we're always looking at the momentum of an entire system. And remember, a system is just a collection of objects. So let's look at our entire overall momentum of this system. Well, that's just the sum of the two momentums. So we add this and we add this. So 1 times 10 to the 3 kilogram meters per second. I'm just going to ignore the value, units for now, just because it takes up space. Plus minus, which just simplifies down to minus 1 times 10 to the 3 kilogram meters per second again. So what am I really doing? I'm just taking one away from myself. So that ends up being a momentum of 0 kilogram meters per second in the overall system, right? These individual components, yes, they do have momentum, but the overall system has a momentum of 0. Now, let's say that after these two collide, right, and they collide in the middle, and what they just leave is a big old, just a cube of crushed car metal. Now, I'm going to say that this is 200 kilograms of worth of metal. Why? Because I have 100 kilogram car, 100 kilogram car. If they collide together, mass is always conserved. So I get 200 kilograms, and it's just stationary, right? They've crashed into each other and they've cancelled each other's momentums out, and so the block is just sitting there. So this is sitting at 0 meters per second. Now, what is the momentum after my collision? Well, that's just 200 multiplied by 0, which is what? 0. So now, let's say that this was P initial, momentum initial, and this is PF, momentum final. This is also 0 kilogram meters per second. So I hope you can understand now why momentum is always a conserved quantity. Now what we want to have a look at is more advanced momentum that you need to know for your triple science GCSE. So let's get right into it. Now I'm going to introduce a brand new concept here called impulse. Now this is where we really start to look at Newton's second law, F equals ma, well, which is part of Newton's second law in the context of momentum and how that really affects collisions. So first of all, let's write down parts of Newton's second law, right? F is equal to ma. Now let's have a look at A. What is acceleration? Well, acceleration is really just the change in velocity, v minus u, over time. Remember, v is final velocity, u is initial velocity. So now let's substitute a into here. Okay, so let's rewrite this equation brand new down below. Now F equals m v minus m u over delta t. Remember, I've forgotten the delta over here, but I'll put the delta now because remember, it's change in time. It's over a period of time. Now what do we have here? Well, mv, does that now look like our momentum equation? Well, which is P is equal to mv. Exactly, it is exactly that. So what that really shows is final momentum. And because we're using the final velocity here, and because we're using our initial velocity here, this is our initial momentum. So what we can really say, what we're doing here is final momentum minus initial momentum. Well, that sounds a lot like a change in momentum. So that's exactly what we can say. So let's put that down below. Is equal to delta P, change in momentum, over delta T. Now let's have a look at what this actually means for collisions. Well, the force exerted by change in momentum is what this equation is really talking about. When two objects collide with each other, they have a very sudden change in momentum. Why is that? Well, because they were going at, say, quite a high speed, and then very suddenly they went to 0. So in a very small amount of time, very small, a very large momentum decrease, because remember they were going at quite a high velocity first. So this means that we get an extremely large force exerted. So now that might be something that we'd want. Say we were using a change of momentum for a sort of like explosion, but say you were in a car crash, would you want the momentum of the actual car, which is going quite fast, to be transferred over a very small amount of time, meaning that you experience a huge amount of force on you? Or would you want the time it takes for the car to actually crash and come to a standstill over a long period of time, so you get a lower force? Well, it's the second one. You want a lower force. And so now what we're going to have a look at is some features in cars that increase the time taken for momentum to change over, to make sure that you receive the lowest force possible. Okay, so now let's have a look at some safety features present in cars to increase your collision time. Because remember, we're looking at impulse here, which is force is equal to a change in momentum over time. Right, delta t. Remember, we want to increase delta t as much as we can to decrease the force exerted on us, the human, whenever we're in a collision. Because remember, our momentum is pretty much fixed, because momentum is really just mass multiplied by velocity. Sure, we could decrease the velocity and or somehow make our car lighter, but these are all things you can do before the collision, not really in the middle of the collision. You know, you can't really just like throw off a door your car or suddenly slow down before you collide, right? We can only really change the time that our collision happens over. So our first one is airbags. So I'm sure everyone knows what an airbag is, but it's really just a sort of cushion of air that comes out of common places where people would be sitting. So out of the steering wheel, out of the dashboard, and out of the sides of the cars, right? So what these are really designed to do is sort of cushion your collision with the actual steering wheel or the dashboard or the side of the car itself. Because remember, sure, you could just bang your head on the steering wheel and you would come to a dead stop very quickly, but that would mean that our time would be extremely small, and so the force you would feel on your head due to, you know, slamming it into the steering wheel would be extremely high, and that would cause you injury. So we don't want that. We want the airbags to sort of cushion our fall onto the steering wheel or the dashboard or whatever, to increase our time, to decrease the overall change in momentum, so we get the lowest force exerted on our face as possible. Now, we also have seatbelts. Now, I'm sure a lot of us have done this, right? You're just sitting in the car, you're bored, and so you tug on your seatbelt. You can feel that your seatbelt goes a little way and then very suddenly stops. Now, car manufacturers could design a seatbelt that as soon as they feel you pulling the seatbelt, even a tiny bit, they just freeze up straight away. But they don't do that. Well, why is that? That's because if they allow the seatbelt to travel a little bit of distance, that gives you a little bit of flex time to sort of like rock forward before the seatbelt catches you, meaning that you get the largest time possible before the seatbelt actually has to stop you. And again, you get the lower change in momentum, and so you get the lowest force exerted across your entire torso. Like, there have been cases where faulty seatbelts have just locked up straight away and they've broken ribs of the actual occupant inside the car itself. Next, we also have something new called crumple zones. Now, a lot of people aren't really aware of this, but this is really in the car manufacturer's design. So I have my rubbish car here, right? I'm not going to win any art awards. Usually, at places where commonly people crash, so the back, the front, and the sides are made up of materials which are designed to sort of fold in on themselves. Now, why is that? Well, we could make these zones extremely hard, right? So that would mean that they wouldn't really break when two cars collide each other. In fact, they might actually just bounce off each other. But what would that mean? That would mean that our collision time is extremely small, because they would just hit and bounce off, sort of like snooker balls, right? You hit one and they just instantly hit off each other, right? But that would mean that an extreme force would be felt by the occupants of the cars. So instead, these crumple zones are designed to sort of bend on themselves, right, and sort of crumple inwards, allowing the cars to hit each other for to stay in contact, for the longest amount of time. And so the contact time increases, overall change of momentum decreases, and so force felt by the occupants also decreases. Now, I've said these three things for cars specifically, but there are also other places in reality where we utilize the same sort of idea. So a crumple zone in real life is sort of like a gymnast mat, right? You get those very thick, fluffy mattresses that gymnasts, if they, fail a stunt, they can fall onto. That allows them to have the longest amount of collision time with the floor, and so lowest change of momentum, lowest force exerted. Another sort of airbag-esque thing is a crash helmet. Crash helmets are filled with spongy material which sort of soften your collision with the inside of the helmet, allowing you to, again, increase the time taken for momentum to change and decrease the overall force felt. So that was a lot of information there, but you really need to understand that any sort of safety feature is all designed to increase collision time, because if you increase the collision time, you decrease the change in momentum, you decrease the force felt by the person. Okay, now let's have a look at this hard worked example. As always, we're going to highlight all of our keywords. A girl jumps off the edge of a shopping trolley, alright? This trolley is stationary at the moment the girl jumps. The girl jumps backwards. Describe and explain, using the idea of momentum, what happens when the girl jumps off the trolley. Alright, so in momentum questions, it usually helps to just draw a sort of diagram of what's happening. So I have a shopping trolley, right? I'm going to try and draw that. Okay, that's good. And then I have my girl right here, okay? And I have that. Now, she jumps off backwards this way. Now, what we want to understand is what happens afterwards. Alright, so if we just use our common sense, right, and we sort of imagine ourselves on a trolley and we're jumping backwards and we let go, well, what happens to the trolley? Well, the first thing that happens is that the trolley moves off forwards. Now, so why does this happen? Well, the biggest reason why this happens is that momentum has to be conserved. Okay, that is a sentence you can always throw into momentum questions and guarantee you'll get at least 1 mark. So even if you don't know anything about the question, throw that in there, you'll get a mark. Alright, so momentum has to be conserved. So what does this mean? So initially, now remember, the momentum of our system, it has to be 0, right? So let's do this in green. Initial momentum of trolley plus girl is equal to 0. Well, why is that? Well, because they're stationary, okay? The girl is just on the trolley and she's just standing there. Both of these objects are stationary, and so anything multiplied by 0, their mass multiplied by 0 would give you 0 momentum. All right, so that's our initial momentum. Now, after the after the girl jumps off, the girl has momentum backwards, and so to conserve momentum, trolley must have momentum forwards. And that makes sense, right? Because if you do a minus plus a positive, right, and that just ends up being minus positive, that will give you a 0. Because if we're doing the same values for momentum, which we will, because again, momentum has to be conserved, if we sum them up, we'll get back to our initial momentum. Because remember, to conserve momentum, final momentum must equal initial momentum. So I hope you understand that now, and if you did, well done, because you can get 4 marks. Okay, so now let's have a look at a hard example in numerical form. Okay, I'll spell numerical wrong there, oops. Right, let's put that in there. Okay, as always, we're going to highlight all of our keywords. So the mass of the trolley is 7.5 kilograms and the mass of the girl is 36 kilograms. So we're continuing on from our previous worded example, right? Calculate the velocity at which the girl moves forward if the trolley moves backwards with a velocity of 1.2 meters per second, right? As I said before, it's always good to draw diagrams in these sort of things. So let's draw our trolley moving backwards at 1.2 meters per second, right? That's close enough. This is 7.5 kilograms and it's moving this way at 1.2 meters per second, right? And our girl is jumping forward. This looks like she's skydiving, and she's 36 kilograms this way with a velocity of unknown. All right, so let's start working out. Now, we know that the equation for momentum is P equals mv, and we also know that P initial, momentum before the collision, is equal to the momentum after the collision. So this is a very important sort of fact, because what we can do is that if we work out the momentum of our trolley, we can use that to work out the momentum of our girl. So let's first work out the momentum of the trolley. That's just 7.5 multiplied by 1.2, and that gives us 9 kilogram meters per second in the negative direction, because remember, it's going left. Now that must mean that our girl, so 30, actually let's do that in a different color now. Our girl must also equal 36 multiplied by some velocity, and that must equal positive 9 kilogram meters per second. Why? Because minus 9 plus 9 is equal to 0 kilogram meters per second, and that's our initial velocity, initial momentum before the collision. Because remember, the girl was just stationary on the trolley, right? So how do we work out what velocity? Well, we just do 9 over 36, and that gives us 0.25 meters per second. And so that is the velocity at which the girl moves forward, positive. And if you answered that, well done, you get 3 marks.